what it is, you have to what you can divide here is that you can divide a word by a byte, right? You can divide a word means 16 bits, that is stored in AX. You can, whatever it is of 16 bit, that 16 bit you can divide by 8, and that 8 bit can be stored in your source. Your source can be your register, it can be your register or your memory location. Okay, so that is what we can have. When I am writing division by BL, that means actually it is taking AX, content of AX divided by content of BL. Okay, um, but so this is 8 bit, so definitely this is actually 16 by 8 division is taken. Okay, but whenever you are specifying this as 16 bit, that means you are specifying this operand, your source is 16 bit. So what will happen, your numerator must be of 32 bit. Now if I am just taking AX, then AX will be just 16 bit. So that's why a combination of DX and AX, DX itself is a 16 bit, AX itself is a 16 bit. So DX and AX, combination of DX and AX is taken as 32 bit, and the 32 divided by 16 is taken. So DX AX divided by source. So so what it is? So two things to make sure here. It is unsigned. That means you are considering your numbers as unsigned numbers. You are not going for the sign, or you are not having the significance of the signed bit. Rather, I should say. Okay, so it is unsigned division. And one more thing, that you can divide a word by a byte or 32 by a word, a double word by a word. Okay, and that is how this is the combination and how this value is stored. So now whenever you have a division, you have two entities generated. One is quotient, another is remainder. So quotient is stored in that lower in the lower function, lower byte or lower word, what we can say, lower double word, whatever you can say. So quotient is stored in AL if your result generated is, if you are taking just 16 by 8, right? So when you are dividing 16 bit by 8 bit, then mostly what will happen, your remainder can be maximum of 8 bit, and 8 bit of remainder and 8 bit of quotient is generated. And that quotient, the quotient is stored in the lower byte, that is AL, and this is stored in AX, right? What next? Sorry, AH. This is stored in AH. And if you are dividing it by 32 by 16, that means 16 bit of quotient and 16 bit of remainder is possible. And this is, if it is a remainder, then it is stored in higher part, and this quotient is stored in lower part. What is lower part? Lower part is AX, so quotient is stored in AX, and higher part is DX, that is the remainder is stored in DX, and 16 bit can be accommodated here, 16 bit can be accommodated in AX. Yes, you can. If you want to divide word by word, then what you can do is that that word should be extended to double word. When you want to divide word, so you okay, if you want here, your source is word, right? But option that we have is just double word. So what you have to do, you have to extend your word to double word. For that we have that instruction, this one, convert signed word to signed double word. In case it is a signed division, of course you will go for, and if it is not the case, then you can definitely take like DX. You should clear DX if it is not a signed one. uh, yes, it is. Yes. So what? In short, if you want to go for word by word, then if it is signed version, of course you are going for the signed instruction. Then you have to use that convert word to double word. And if it is no, unsigned version, then no need to worry about. You just simply make them that make this word double word. I mean word as 0. Keval, is it okay? Fine. Okay, so that is fine. That you can definitely go for that one version. And again, if you want to go for byte by byte, the same logic is applicable here. Byte, so your source is byte, and hence you have to extend it here. Signed version, then use that instruction, convert byte to word. If it is signed version, of course instruction will not be div, it will be IDIV instruction. The instruction will be IDIV instruction, right? So that for sign, and if it is unsigned, no need to worry about, you can just take this as a byte, but AX in that AL must be your data, AH must be 0. That's it, otherwise it will work. Now suppose it is possible that sometimes by some logical error, or by some mistake even, or rather I should say sometimes some unexpected way, when we are writing a program, when we are debugging it, it is not a finalized program, it is possible that sometimes our source becomes 0, that means division with 0 that might come across. Maybe not intentionally, unintentionally, sometimes intentionally even, right? So if that happens, that if you want to divide it with 0, then what will happen? So what is the expected result when you divide it with 0? So you know that quotient will be too large to fit in the destination. It will be larger than, it is infinite, right? The quotient cannot fit into the destination register. At that time, an interrupt will be generated. That interrupt is type 0 interrupt. Okay, this of course we are going to study in detail, but currently whenever you will use that division instruction in the laboratory session, and if you will provide your source 0, it will show you like type 3 interrupt is generated, that type of that type of that unexpected interrupt is generated, kind of error, that notification we are getting, such notification we will get for type 0 as well, like unexpected breakpoint kind of instruction comes when you write interrupt 3, right? You end your program with interrupt 3, that you remember, that is, it is type 3 interrupt, and for that you are having some notification whenever this is encountered, it is having that unexpected breakpoint kind of thing, some notification is coming. For the same way, whenever you have division instruction and that source is 0, at that time not type 3 but type 0 interrupt is generated by default internally, and that's at the time also you will have a notification that type 0 interrupt is generated. So whenever you have that notification, just check that you are having your what you can say, your some of the I mean your, so somewhere the division is divided, I mean your division operation is resulted into infinite. Okay. um, uh, no, it is not. But right now we no, it can be used for other uses also. And what we can say, that what is the purpose of type 0? That whenever your quotient is too large to fit in the destination, type 0 is generated. You can modify it. You can use for the other purpose. But we will study them when we will study interrupt. Right now, of course, we are going to modify this as well. In future, we are going to modify this type 0. Okay, but right now it will be too early to discuss regarding to that. But right now what you have to understand, where whatever you write here is type 3, same way type 0 is there, type 1 is there, type 2 is there, type 4 is there, right? All the types are there, we can use them for different purpose. And right now we will use type 0 for division, and that is sufficient for you to know now. Of course, in future we will explore it more. So now what we will do, in flags are undefined for the division, as in the multiplication, these flags are undefined, right? Here I division instruction is nothing but that's the same one, that just a word by byte, but both are signed version. Same way double word by word, but both are signed, and this is how you can specify. I told you your source can be a memory location as well. Okay, so in both the cases that is true, the both the instruction it is true, right? And here that CBW and CWD instructions can be useful whenever you want to go want to divide byte by byte, or word by word, right? So that we have already discussed. So this is all about division, and all arithmetic instructions we have completed. Now we need to go for some what you can say, some logical instructions, right? Before we go to, okay, let us complete the logical instruction, then we will discuss some logical questions, and then we will go for the next task. Logical instruction is nothing but AND instruction. What it will do, that AND instruction will perform bitwise ANDing between destination and source, right? Your destination and source, what it can be, both can be. Your source can be memory location, register, or immediate data. Your destination can be memory location or register. Your destination cannot be immediate data. Okay. So what will happen, that ending between source and destination, and store at the destination. Ending bitwise end between these two, and so so what you can do is, suppose you are your value of AL is, you are storing this value to AL, right? 8-bit in binary you are representing, and if you want to represent in that H, you can easily represent it as 0 AEH, right? That is okay, where whatever you want to specify, that is A and E, right? So that is okay. You can, if you want to represent in binary or hexadecimal, something is stored in this, and ending your source, you are ending it with immediate this data. What will be the result? Can you tell me what will be the result? What will be the result of this ending? If this instruction is executed, then we will go for the flag. Yes, it will be 1010. And what about this 0110? True. That is bitwise end. You can say this is 0, this is 1, this is 1, this is 0, this is 0, and this is 1, this is 0, this is 1, right? Bitwise ending. Right. So I'm okay. Yes, I think all of you are comfortable. True. So this is bitwise ending that we are performing. Yes, I'm going to share the PDF, but right now, uh, uh, as I told you, many information is not given here. So you should try start making your notebooks and start reading from the books available. Any standard book available. Just note down the topic, read from the whatever trustworthy source you find. Okay. Of course, I will share this, but do not wait for this. Start reading and start noting down as you were used to do in the classrooms. Okay, so what is this? That CF and OF uh, both are zero after end. So here's CF and OF, that is overflow flag and carry flag, are not updated as per the result. They are zero after end operation, right? While PF, SF, and ZF are updated as per the end instruction, right? AF is undefined, and of course PF is related. PF is what? Parity flag. It is whatever the ending you do with 16-bit ending or 8-bit ending, PF will be updated just by 8-bit. That is how it is defined. Okay. So what is the conclusion? CF and OF are zero every time. AF is undefined. PF, SF, and ZF are updated as per the end instruction result. And PF, when the result we are discussing, result can be 16-bit, but the 16-bit, what instead of 16-bit, it is going to use just 8 bits. Okay. As I told you, this is what we can have. Like both this, your source can be memory location, immediate data, or your register. Same way, this can be memory location or a register. Same way for OR instruction, what it is, um, CFOF are 0, PF, SF, ZF are updated as per the OR instruction, AF is undefined, PF is defined for last 8 bits. It will do bitwise OR, destination and source, so same as AND. XOR, again the same thing, right? You can see it is the same thing, and it will perform bitwise XOR operation. And not, what is not? Just not and destination. So what will happen here, that you have to specify your data 8-bit or 16-bit. It can be register or memory location. AF is auxiliary carry, auxiliary carry flag. So this is not instruction. Okay, so that is all about not instruction. I mean, that is, it will just do bitwise. I mean, not bitwise, not 1 is 0, 0 is 1. So I don't think much information is needed here. Any doubts so far? Any doubts so far? Okay. Now, now what is? Let us have one example of checksum. Do you know what is checksum? Do you know the concept of checksum? Quickly answer yes or no. Possibly you might not know. Have you heard about checksum? Okay. Okay. What is checksum? That generally when you transmit data, right? When you generally transmit data, so what happens? Like you are sending that one, then 101. This is how you are transmitting data. One, any random data you have, right? Now, how will you verify whether the received data is correct or not? Yes, it is a message validation method. True, it is a message validation method. Let me explain those who are not aware of. Suppose I have a source, I have a destination. I am sending some data to source to destination, and that data is binary and it is represented like this. Okay, so how will you be sure that received data is correct here? How destination will validate that message received is correct? Okay, so for that, what destination, what source does that, whatever data it has, suppose this is the data, it breaks it into chunk of certain bits. Suppose I am choosing a chunk of 8 bits. So whatever data I want to send, I will divide it into chunk of 8 bits. So this is one chunk, and this is second chunk. Of course, this is 6, so I will add 2 more bits. Assume that it is 8-bit data. Okay, so I have divided the available data into chunk of 8-bit. Okay, so and then what I will do, 11010. So then I will add them. What will happen? Then I am going to add them. But what I will use, I am going to use to add. What is checksum? What is that? You just sum it up. Okay, so suppose I want to send, suppose my one data is 5, suppose it is 5, another data is 13. If I add them, what will be the result? It will be 18. Then what I will send here, I am going to send what we can say negative of this. That means I will send minus 18 with my data. So what actually I will send? I will send 5, 13 and minus 18. This is what I will send to my destination. What destination will receive? 5, 13 and minus 18. What is the job of destination? It will sum it up. That's why it is checksum, right? So what it will do? It will sum entire data. Here useful data is 5 and 13. 18 is a checksum. Okay. But instead of what is that checksum? Checksum is nothing but summation of this two and negative of that value. Okay. So actually I have sent 5, 13 and checksum, that is minus 18. Okay. Now destination has received this. What is the job of destination? To sum them up. What will be the summation? If the destination sums it up, what will be the summation? If it adds 5 plus 13 plus minus 18? Yes, it is 0. So if the summation along with checksum results 0, that means received data is correct. But suppose LSB of this is corrupted. 5. What is the LSB of 5? If what is the LSB of 5? Least significant bit of 5. If you represent 5 in binary, what is the least significant bit? Yes, 1. Suppose it is corrupted. What is the meaning of corrupted? It is changed. Suppose 1 is changed, so it can change to which value? What is the possible value? Just here, yes, it is 0 possible value, right? I mean, no, not yes, it is yes. So now the data will become 4. Because last data was 101, like this was 101, and if I'm representing in 8 bits, so also you can represent it in 8 bits like this. So this is my value 5, but this bit is corrupted, so now it has become what we can say, it has become 4. So now in the channel it is corrupted and it has become 4. So now what is the received data? This only one bit is corrupted. What will be the checksum? So this was transmitted. The checksum was 18, right? This was correct at the source, but it corrupted in the channel. Somehow noise occurred and it corrupted here. So LSB of this was corrupted. So what will be the received data? Received data will be 413 minus 18. Is it okay? So what will be the checks? What will be the checksum here? What will be the summation here? Minus 1. Will it be 0? No. So will destination validate the data? Will destination validate the data? What it will think? It will come to know it is corrupted data, right? Because something is corrupted, some data is corrupted. Because checksum, which was calculated based on whichever data, that data, same data is not received. That's why summation is not 0. Are you following this, all of you? Okay. Now, how it is actually implemented? How it is actually implemented? This summation is actually performed using XOR. The summation is performed using XOR. Understood? So that is now question is 2, that find out checksum value, this value, 18 value, summation value, using suppose two data is stored, two words are stored in my memory. Two words are stored in memory. Okay, and find out its checksum. So first of all, let us find out sum. Then we will go for checksum value. So what it will be? What it is? So can you tell me how it is? How will you perform that? Suppose two words are stored. This is stored in memory N1. This is stored in memory N2. So now what I want to do is that I want to perform XOR between these two. So what I want to get is this. What will be the XOR here? This will be 1, this will be 0, this will be 1, 1. What will be this then? This will be 1, 0, 1, 1. Okay, and then, and what if I add all three? What is the result if I add all three? Suppose I am taking this, I am taking this. These are my two words N1 and N2. What if I add all three? This is my XOR. Yes, everything will be resulted into 0. So can I say this is my checksum? Like I will send N1, N2 and XOR. So this will result into my checksum. Are you following that? Okay, so now give me the program. I want write a program. I'm not going to write. It is not difficult. Two words are stored in N1 and N2. Okay, and now stored this type of result. That means whatever the transmission ready data. Okay, you have to store transmission ready data to a certain location. Say you have to start. You just store it at certain location. I mean, set this in certain other location, adjust this to certain other location. So take this data from one location and store this as whole at other location. I mean, you can use 3 locations. Of course, you will need 3 locations. So write a program for that and give me that program. What you have to do? At location N1, something is stored. At N2, something is stored. Take this two and transmission ready data. So I will write it as other location is ready data. Did you learn to okay, ready byte 1, location 1 is ready byte 1, ready byte 2 and ready byte 3. These three locations are there. You have to store this to that. Quickly give me the program. No need to verify, just briefly if you can tell, give me. Just tell, give me what will be your data segment. First is important thing is data segment. If anyone has completed data segment, okay, XOR instruction is this. Destination and source is needed, no? N1 into, no, Ronak, what is RB1? RB1 is a location where you have to store ready byte to transmit. The byte that is ready to transmit, that you have to store there. So first of all, I want to store it like N1, N2, like I was sending 5, 13 and 18. So in that way, I will send N1, N2 and XOR. Whatever your result of XOR is, that is stored as ready byte 3. RB1 will have N1, N2 and this is your XOR. These are memory locations. Okay, Ronak, are you clear with it? What I am asking is, first of all, how will you define your data segment? How will you define your data segment? Which are the things that I will write, okay, data, then segment, right? That is okay. I'm not writing it, data and segment. Then, first of all, you will write N1 here. Then what will be next? Quickly, what will be the next one? Yes, it will be DB and whatever data you have, that data you are going to write here, right? Suppose I am writing the same one here. It is, what is that? It is D3. So I have to write 0D3, that you know, na? Do you understand why I have written 0? Okay. So 0 D3, because you cannot start your number with alphabet, so you have to start with 0. N2, what is N2? So it is DB again and it will be 0 E H. Okay. What about RB1? What I have to write as RB1? It is also DB, but I don't know what will be the data. Have you used this question mark ever? Yes. Right. Same way RB2, DB question mark. So I will store the data there. And RB3, okay, and question mark. And data ends. Then code segment, that assume, then move AX data, AX to DS. I'm not writing those steps. They are common. What I will write as content, where I should take N1. I will use XOR. Can I write XOR N1, N2? Actually, I want to perform XOR here. Can I write N1, N2? No. So what I have to do? Okay, move AX N1. AX, do I need to use AX? Yes, AL. So yes, it will be move AL or AH, whatever you want to do, but not AX, right? N1, right? Then, so I will write XOR AL with what? XOR AL with N2. True. XOR AL with N2. And whatever the result is stored, where is the result? Where the result is? Where this result in AL. So what I need? Where I need to store it? Where I need to store the result? What is my expectation? RB3. So what I will do this? What will be my next step? What is my next instruction? Move AL where? Yes, to RB3, true. And then it is very easy to move data, N1 data. So now what will happen? Yes, now it is, I think, easy to move this N1 to take N1 in AL or AH, wherever you want to take, then move AH to RB2, RB1, right? So RB1 and AH, then take in AH, take data from N2, then RB2 and N2. I hope you are following, sorry, AH. I hope you are following. These are all move instructions, right? All are move instructions. Okay, so this is how you can perform, you can write. So what will happen now? Transmitter simply read from RB1, first data, second data, checksum. Then again, suppose next data you want to transmit, you will store it at RB4. Then N1, N2, it's checksum. Then next data if you want to transmit, then it will be then further. So what the transmitter is, that circuitry of transmitter or the block of transmitter will do, it will simply read this memory location onwards. So now it is easily available, this data N1, N2 checksum, N1, N2 checksum. Okay, now we have to, suppose we want to verify the checksum at register, suppose we want to verify the checksum, what can be the steps? Suppose you want to verify the checksum. So what to do? So what will be available to you? N1, N2 checksum. Suppose it is available to you. And you have to see whether the received data, so received data you have stored in N1, N2, and checksum is stored at this location. Suppose this is the receiver side, and N1, N2, and checksum is available to you. How will you verify? So first of all, what you will do? You will take N1 data to AL, then you will perform XOR with N2, AL and N2. Now this XOR is already in AL, then you will take, then you will perform XOR. I mean, you will RB1. Sorry, you will take RB1 first byte, then you will take RB2, and then XOR AL with RB3. What should be the result now? What should be the value of AL? This value of AL should be 0. So this will be the program at the receiver side, right? So yes. So how will you verify whether this checksum is correct or not? Yes, jump if 0 flag is set. True. So that type of instructions yet we have not studied, but will be useful. So 0 flag will be set, and we are going to use that 0 flag, and that will help us. Okay, so this is all about logical instruction, and this is how they are useful. So which programs we have taken to calculate checksum and to verify checksum? Those two programs we have included here, which are of course not mentioned here, but of course I hope you have noted down. Okay, so fine. So that is all about uh, not operation and use of them. So how this is how and or not instructions will be useful to you. Now compare instruction. Suppose it is comparing source and destination, right? I think this concept you have studied, compare instruction you have studied in the 8085, right? If destination is greater than source, then which flags are set? If destination is equal to source, then which flags are set? And destination is less than source, then which flags are set? Have you studied this compare instruction? Do you remember? Yes or no? Do you remember it? Okay. So how exactly this compare is taking place? How exactly it will take place? Do you remember or not? If okay, you remember, but you don't remember very clearly. Is that the case? So see, actually, what we just you have to remember what, right? whenever we have CMP, D and S, destination and source. What exactly does destination minus source? It does so. Destination minus source. Okay, this minus this. Okay, so now both are equal. Then what will be the subtraction? Yes, both are equal. Then 0 is set. True. So both are equal. That means it is result is 0, and hence 0 flag is set. Okay. Suppose this is larger, or rather this is smaller. D is smaller than S. Suppose D is smaller than S, then what will be the scenario? What result will be, positive or negative? Result will be negative. So what will be carry flag? What about carry flag? Because see, carry flag is what, that the destination whenever it is a negative number, right? So what will happen? Um, uh, okay, so carry flag borrow will be generated, right? Because it is a negative number, so that carry flag will be set. And what about sign flag? Negative number, because it is a negative number. What will happen to sign flag? Sign flag will be 1, because negative number, that means sign flag will be 1, and borrow will be generated. That's why carry flag is 1. Okay. And suppose whenever this is larger, when D is greater than S, that means what about sign flag? What will be subtraction? When D is greater than, subtraction will be positive, and hence sign flag will be 0, and borrow will not be generated, and hence carry flag will be 0. So simply you have to remember, actually it will perform subtraction operation and flags are affected accordingly, but the result is not stored in destination. I mean, D and S contents are not modified, just flags are affected. All the flags are affected based on the subtraction operation, right? Just flags are affected, not the destination. Okay, so that is, you can compare with immediate data 8-bit, or you can compare with 16-bit, or you can compare it with the memory location as well. So immediate data, register or memory location, this can be register or memory location. Okay, any doubt up to this in this compare instruction? So here, if you want to, check here, if you remember, suppose you don't want to perform last XOR, you want to verify whether this received data is correct or not. Then what you can do, you can find out XOR, you can find out the checksum using RB1 and RB2. Now result is stored in AL, which is nothing but, yes, you can compare AL with RB3. True. That is also fine. That will also work here. Okay, like, because the result itself is a XOR, that is what is stored here. If both are same, that XOR of this two and this, then also it is working well. The same, this instruction also can be replaced with compare AL RB3. I hope it is making sense to you. Anyone having doubt up to this? I can repeat if not clear. I can repeat anything up to this if not clear. So should I move to the next one? What about others? Should I move to the next one? Are you clear with? Yes, if D is equal to S, then 0 flag is set, because subtraction will be 0, no? So result is 0. So only 0 flag is set. Of course, carry flag and sign flags are also 0, because see, what will happen to carry is not generated, so carry status is also 0. And what about sign flag? Entire result is 0, so 7th bit is also 0, or MSB is also 0, and hence it will be 0. So these two are 0 at that time, but we will use 0 flag to decide it. Anyone is having any other doubt? If it is fast, you can tell me. Is it clear doubt? Is Dev? Is it clear? I mean, is it clearing your doubt? What what about others? Are you clear with it? Answer can be yes or no, so that you can go quickly to the next one. No? Okay. Deep and Keval are answering. What about others? I need participation of you all. No? What is the problem in writing yes or no? If not clear, tell me no. Okay. So, fine. Don't hesitate to answer or don't hesitate to ask. Right? Fine. So, I assume from 2, 3 answers, I mean feedbacks, I am assuming that all of you are clear. Okay, no issues. Now, write a program to um, perform, I mean, to verify De Morgan's law. What is De Morgan's law? What was De Morgan's law? First, tell me. Do you remember De Morgan's law? It is not difficult. No? Last time you studied, last to last time you studied. What was that? A or B is what? Yes, A or B. Yes, A or yes, it is true. So that is what you have to verify. So quickly write it. It is A plus B naught of that is equal to A naught and with B naught. So where you will have your data, A and B are stored in certain memory location. So anyone can give me the data segment? Can anyone copy in the chat box that data segment? True. That will be A has data, B has a data, and the result is stored in third location. We might need it, so or in advance that are reserved. Okay, that is good. So P has two data A and B. Now then we will. So this is what your data segment will be. Assume that A, B data is stored and two locations are reserved if we will need, right? Then what about code segment? Then for the code segment we have codes that that code segment and that assume line, then movement of DS, and those 4 lines are always common, so I'm not writing those lines, right? Then can you tell me how will you perform? How will you check that? So first of all, you will take and that A2. What will be that? A you will take in. Yes, you are going to take it in AL. True. B you will take in. Where you want to take BL? I mean BL. Okay. Right. Then you have taken those two. Then what you will perform? Or. Right. ALBL. What is the next step? Yes, it will be not AL. True. Not AL is remaining, ne? Prince. A plus B dash of that, right? Okay. Then true. Then whatever princess is correct. That AL2 result 1, right? What next? What is next one? Again, take A in AL. Huh. Then what next? What next? Not AL. Yes, not AL. Already B, not BL, because already BL has that data. Not BL is next one. What next? And ALBL. Yes, it will be true. Yes, it is and ALBL. What is the next step? Compare. Why compare ALBL? Preet? Or AL has what? AL has your right hand side, right? Ha. Compare AL with result one. Compare AL with result one. Okay. And if zero occurs, then it is if zero occurs, then and then you should then if zero, then jump if zero, JZ or JNZ kind of thing we will need. Okay, so this is how you are going to verify. What you will do, so now you are having result in AL, that is right hand side, right? Then you will have compare AL with resistor, I mean result 1. That will be result 1, right? Compare AL with result 1. I hope you will this result 1. Okay, compare AL with result 1. And if results are equal, then JZ to some location XYZ, right? That XYZ will indicate, will do some task if they are equal, right? Or if they are equal, then um, I mean, this is where it ends. Of course, whenever we will have loop instruction, um, if they are equal, then zero flag will be set. Up to this is sufficient. When we will go for JZ, JZ will do some. If it is zero, that means XYZ location will do a task if the De Morgan's law is verified. It can be a printing. It can be setting some resistance, right? Kind of thing. Okay. Now, what about? Okay, so this is all. This is how it can work. Now we have a next instruction, that is test instruction. What is that? It is AND operation, but it will not modify your destination. Otherwise, it is AND operation itself. Just only thing is that it will not modify the content of your destination. So far, what was happening? That AND ALBL, then AL was modified as per the result. Now what will happen? Just flags are affected, not destination content. That is what the test instruction is. Flags are updated, no, neither of the operand is changed. Any doubt up to this? Okay. Now, one question is to you is that which are the instructions, which are the instructions that can clear your accumulator? Tell me the instructions that can clear your accumulator. Accumulator is what? Which register is known as accumulator? AX. Keval, it will be AX, entire 16-bit. Okay. Okay. So what are the which instructions are there to clear your accumulator? I want to make it 0 because I want to restart my operation there. So what are the options I have? Uh, Give me the entire instruction. Move is one of that. XOR. They tell me the entire one. Move AX000H. Yes. Subtract A. Okay, well, how compare AX with AX? What I want to clear accumulator. I don't want to set 0 flag. Are you getting it? Subtract AX, that is true. XOR is also true. Yes, XOR AX is also true. And with AX as all zeros is also true. So there are, yes, true. Any other idea that you have? All of them are correct method, like XOR AX and AX000H, move AX000H, subtract AX, comma AX. I mean, both you have to specify, right? So it will be subtract AX, comma AX. That is also true. Any other idea that comes in your mind? Multiplication. Can you use multiplication instruction? In multiplication, you don't need to specify AX. You can simply write MUL 0000H. I mean, AX is default one, right? AX is default one. Okay. So, true. So, what is the point here? The multiple instructions are possible to perform a task. Now, tell me, out of all this, which one are you going to use? Move. Why? Why, Jenny? Okay. Urjit also says move. Why move? What is a specific reason? No flag update. Okay. Okay. No flag update. But I mean, whenever, okay, so if that is a constant that you don't want to change your flags, then of course you can go for this. If constant is that flag is okay. Why, Vimal, you are going for multiplication? Jenny's reason is that he'll go for move because no flags are affected. I agree that if it is required that flag should not get affected, then you should go for this. Short instruction. How it is short? How have you decided it is short instruction? You need to specify immediate data 000H. No, no, not like that. See, how it is, that is what my Vimal, you are correct up to some extent that we should go for the short instruction. But you are incorrect in the way that multiplication is a short instruction. See, we are specifying MUL, then we are specifying 000H. So how it is stored in the memory? How it is stored in the memory? So it is stored like multiplication operand is stored, 00 is stored, 00 is stored. So it is actually at least 3 byte, right? So it is not like if I'm not specifying, if I'm writing even move AX comma BX, then it is, though I am specifying both the operands, but still it is 1 byte instruction. Are you getting, Vimal? Is it clear to you? It is not like number of operands you are specifying. The data you are specifying, this will go into one opcode itself. Okay. So, yes, all of you are correct here that for move, it will be, no, it will not be 2 cycles for move. Actually, 00, it will also be move 000H. So, 3 locations needed. 3 cycles are required, right, to extract from the memory. Move directly, so again, so not 2 cycles, move directly copies, while other instruction we have to do operations. Which operations we have to do? Directly copies. Copy is also one operation, no, Urjit? Okay. So, fine. So, if you are saying that again, but I don't think that copying and performing that ALU part will be so quick. So, of course, if you are going for the nanosecond timing, and if you don't want to, but again, see, whenever you are, see, what you have to do here, I will not agree with you, Urjit, here. What is the case? What you are saying that uh, what it will do, it is reading the data 00 from somewhere. It is reading the data 00 from bus, right? It will need this immediate data. It has to deal with this immediate data. It will be available from the buses, right? It has to read from the memory. So what will come? That 00 data, it will read from this memory. What to move? So whatever data is specified in the memory, that you have to put in the bus, and that data will come to your ALU, and that ALU is going to copy that data to your register. So what you are doing? You are writing move 000H, but that 000 is stored in memory. So ultimately, you are reading that 0000 from the memory twice. Understood. While if you are doing XOR, in that both the operands are available in register. Registers are nearest to your processor, nearest to your ALU. So that operation, though you are performing XOR, it will be quick. Are you following? Because everything is available here. You don't have to go for memory there. Understood. So definitely, what is our conclusion here? You all of you are on the correct path, that we have to deal with the size of the register. I mean, size of the instruction. But how to decide what will be the size? We have to understand how exactly. I told you that it is stored as 3 bytes, 2 bytes, but that we need to understand how these instructions are stored in bytes. So actually, you are converting your assembly language to a machine language, or rather, I should say, you are representing it as a numbers. Your instructions are represented as numbers. Okay, so that is what our next topic will be. That instruction format, how it is 2 bytes, how it is 3 bytes, how it is converted, that how move instruction is converted into numbers, and all those things we are going to discuss in the next lecture. Okay, so from that you will come to know what will be the size of it will be 2 by 3 byte, and where it will go to memory or not, whether it will go to memory or not, and how much time it will take, kind of things you will be able to judge from the looking at instruction itself. Okay, so that will be the next topic the topic on the next lecture. Any doubts so far? And yes, all of the ways are correct, but I should go with wherever the size is, number of bytes are less, it will be like, wherever immediate data you don't have to specify, that will be the best instruction to perform with. So I will go with XOR, right? I will not go with AND, move, and that other instructions where multiplication, where I have to specify the operands in the immediate data. Yes, subtract and XOR is fine. Subtract and XOR is fine, provided flags affected is not your constraint. Okay, so I'm stopping my discussion here. Any doubt, in case, you can ask me anytime.
How the concept of assembly is helpful in